So in my slides here, I'm going to talk about debugging and understanding NLP models. And this is how to tell when, for example, both your implementations are wrong and, for example, your underlying assumptions are wrong, or your model is failing on particular segments of data or stuff like that. So I'm going to go through a variety of things that can go wrong with your experiments, basically. So a typical situation is you've implemented some NLP system, based on neural networks, of course, because that's what we use nowadays. And you've looked at the code, it basically looks okay, but it has low accuracy or it makes incomprehensible errors. And you would like to fix these, or you'd like to improve the accuracy or something like that. And so what do I do? And I think there's 3 dimensions of how you can understand your model and your model behavior. The first one is debugging the implementation. So it's identifying problems that you have when you implemented something. Second thing is actionable evaluation. So identifying typical error cases and what you can do to fix them. And finally, interpreting predictions or interpreting what's happening inside the model. And this can maybe give you a deeper idea about what's happening in individual cases. And there's a lot of reasons why you might want to do that. Both like to make your models better, and also, for example, if you want to be sure that your prediction isn't doing something illegal, like discriminating against people due to protected attributes or other things like that. So there's a number of reasons why you'd want to do that. So I'm going to talk about the first 2, and Nishant is mainly going to talk about the second one. So going right into it. So in neural network models, debugging is really important because they're opaque, they're unpredictable, and if you make little mistakes, they can cause big problems with your output. And another thing is that everything is a hyperparameter, including your network size, your model variations, your batch size, your strategy, your optimizer, and your learning rate. And finally, unlike kind of more traditional machine learning methods like logistic regression or support vector machines or something like that you might have studied in your machine learning class, stochastic optimization has no guarantees about convergence. Your loss might go down, then it might go up, and there might be absolutely nothing wrong with your training, or it might be, a serious problem. So that's another issue you need to deal with. So first, I'd like to go into possible causes of problems with your implementation. And I'm going to break them down into a typology. And based on what part of the typology you're running into problems with, you will need to fix them in different ways. So your first goal when you're experiencing the problem is identifying why you're experiencing the problem, because that will lead you to a solution. So for training time problems, there's a bunch of things that could be wrong. The first is a lack of model capacity. So your model is not able to model the phenomena that you want to model in the first place. You could have a poor training algorithm. You could just have a bug in your code at training time. Another thing is test time problems. And these can include a disconnect between what you're doing at training time and what you're testing at testing time. Failure of search algorithms. And another thing you'll want to deal with is overfitting. So you're actually doing well on the training set, but you're doing poorly on the test set. Finally, you could have a mismatch between the function you're optimizing at evaluation time and what you're actually evaluating. Sorry, the function that you're optimizing at training time and what you're actually evaluating at test time. And my best piece of advice for figuring out why things are going wrong is don't try to do all of them at once, and rather start from the top and work it down, because the ones at the top are often easier to diagnose than the ones at the bottom. So looking at how you can debug systems at training time, there's a number of ways you can do this, but the most important thing for training time issues is looking at the loss function calculated on the training set. And what I mean by this is don't look we talked about how we can't optimize error or accuracy easily, so instead we optimize likelihood. And so you might want to look at accuracy to see whether your model is working well, but I would urge you first to look at your likelihood or your loss function on the training set instead of your accuracy on the test set, for example, to diagnose these variety of problems. And the sorts of things you want to look at are, is the loss function going down? So is it, converging into a good place? In general, if this is your loss, the first thing you should know is like, what is a good loss? In most cases, a good loss is zero. Like log likelihood, the best loss you can achieve is zero. So you have zero down here. Something like this is essentially a good loss function. Something like that, especially if this is a relatively high number, is usually a bad loss function. Something like that on your training set is a very bad loss function. Something is going seriously wrong. If you see this on your dev set, that could be, or your test set, that could be overfitting. But if you're seeing that on your training set, that's usually symptomatic of a problem. So these are things that you should be knowing. Is it going down basically to zero if you run training long enough for many epochs over your training data? So if it's not going down to zero and it's sticking up here, then that's also an issue. And if it's not going down to close to zero on whatever training set you're training on, let's say you make your training set extremely small, at least in that case, it should go down to zero. Otherwise, you might have a serious problem in your implementation. So these are good things to check first when you're training a model. And there's a number of reasons why this might not be helping, or why this might not be happening. So your model might be too weak. And so in general, larger models tend to perform better, especially if you're using a pre-trained model. And this is just an example from the T5 paper where they scale up the T5 model from a relatively small model to what at the time was a very large model of 11 billion parameters. Now this is, moderately sized model or maybe even small model by some standards. But anyway, you can see that it continues to increase. One really interesting phenomenon is that actually larger models can learn faster, or at least with fewer steps than smaller models. And so this is an interesting example. This paper on neural scaling it's a very influential paper, but basically what they show is the darker purple ones are smaller models. The yellow ones are bigger models. And what you can see here is the purple model, and on the left side, they have the number of tokens processed. On the right side, they have the number of compute, or the amount of compute. And so what you can see is if you just look at the number of tokens processed, the larger the model, the faster it converges, which is maybe a little bit surprising, maybe a little bit, or maybe like some people have the intuition that this should be the case. But when I first saw this, I found it a little bit surprising because I thought it would be so large and noisy that the model would have trouble fitting the data as quickly. But there's actually a good reason for this. Does anyone have a guess about why this is the case? We've talked a little bit about the underlying phenomena for this in previous classes, so you might be able to think back to some of the things you've seen. Yeah. Yeah, so just to repeat, there's a lot of different parameters, so it can try to converge along a lot of different dimensions. So if we think back to the model pruning class and other stuff like that, part of the reason why we can prune large models so efficiently is because only like a small number of the parameters are actually useful. And so if you start out with a much larger model, it's more likely to have useful subsets of the parameters, basically, which is called the lottery ticket hypothesis. There's a famous paper called the lottery ticket hypothesis that examines this phenomenon. So one interesting thing is you can see that even if you scale up the compute, even if you measure based on compute, the larger models eventually surpass the smaller models in terms of how efficient they are at modeling the data. And that's just because models tend to learn well for a while, and then they basically reach their capacity and stop learning well, or they start learning very slowly. And once you get to that point, the larger models work better. So there's a kind of counterintuitive thing that if you want to train faster, you actually can train a larger model, and that will get you to a good solution. At some point, that will get you to a good solution faster than a smaller model would. You know, of course, you need memory and stuff. But
why are you looking at the text field? Like, are you punching on a different data field? Like, isn't that training?
so this is test loss. Training loss also looks like this. I think on this particular paper, they never repeated data. And if you never repeat data, actually your training loss looks very similar to your test loss. Because if you can assume your training data set and your test data set are identically distributed, your training loss of new training data should be exactly the same as your test loss. So I think that's basically why they were justified in doing that here. But they probably did test loss to like assuage the concern that this was overfitting to the training data or something. But good question. Cool. So these are good things to know. So basically, if you see your model doing something like this, plateauing out, maybe your model's too small and you need to train a bigger model, basically. Another piece of trouble that you can have is trouble with optimization. And basically, you should check your optimizer. Usually people are using Atom variants nowadays, like Atom or Atom W, so just use that. Learning rate, so make sure that the learning rate you're using is standard for kind of the model size that you're using. And the best way to do this is look at previous papers and see what they're using. Initialization, most people nowadays will not be training from scratch, but if you are training from scratch, how you initialize your model is really important. And normally the way you do this is you do this with some sort of uniform random noise. And specifically, you can pick the uniform random noise in intelligent ways based on the data size, which I'll talk about in a second. Also, mini batching. Are you using sufficiently large batches of data? If you're using small batches of data, you might have too much noise in your training and it might diverge. So these are things you need to think about as well. Cool. So these are training time things. The next thing is debugging at test time. And this is particularly important if you're doing any sort of, like, I guess a lot of this has kind of been commoditized and it's implemented in Hugging Face and stuff like that. And as long as you're using the standard implementations, you're less likely to run into these bugs. But if you are implementing anything on your own, this is actually really tricky and you can easily make mistakes. So it's important to know about it. So one of the reasons why you can have training and test disconnects, especially if you're doing something like text generation, is that usually your loss calculation and prediction functions will be implemented in different functions. And like anything in software engineering, this can be a source of bugs. Duplicated source code can be a source of bugs because you might implement one thing in one place in one way, another thing in another place in another way. So this is no exception to that. It's especially true for structured prediction models. So anything where you're not just making a single prediction, but you're making multiple predictions in a row. So you need to be a little bit careful about that. Another thing that you need to pay attention about is often, especially if you're doing your own implementation, loss calculation is mini batched and generation is not, or in highly optimized versions of inference, you might be doing inference with dynamic batching and stuff like that, and it might become complicated and you might make mistakes. So how do we make sure that we're not making any mistakes here? There's a really simple way to debug any sort of mini batched loss calculation, because normally when we mini batch loss calculations, we're simultaneously calculating the loss for like 4 or 8 or whatever sequences at a time. And so you can calculate the loss with a large batch size, like 32, and then calculate the loss for each sentence individually and sum them together. And these values should be the same. And this can help make sure that you don't have any, issues with your padding or your masking or other things like this. So this is particularly important if you're not just using out of the box things, like you have a slightly unusually structured model with like hierarchical encoding or anything like that. You need to be really careful about that. You can even create unit tests that test this. So like in machine learning code, we don't write unit tests, or especially neural network-based machine learning code, we don't write unit tests that often because it's kind of hard to do. There's lots of randomness and other stuff like that. But this is one thing that you can easily test and make sure that you don't have any mistakes in. Any sort of generation algorithm. So when you're generating or decoding, you can make sure that your decoding code is getting the same score as when you calculate the loss. And an easy way to do this is you call the decoding function to generate an output. And normally when you're doing any sort of search or sampling or something like that, during the search or sampling, you're calculating the logits or the log probabilities of each step that you sample. So you keep track of that during your sampling algorithm. And then after that, you call the loss function on the generated output, and you calculate the loss according to the loss function. And the score of these two things should be the same. You know, you do your generate, and that gives you an output and score. And then you do loss on the output. And that gives you score 2. And then you just compare these two things together. And this can, in my experience, this has allowed me to find the majority of the bugs in these two things. Have allowed me to find the majority of the bugs whenever I was doing any sort of like complex thing with respect to generation or models and stuff like that. So it's a very common place for bugs, even if you're pretty familiar with models. So I would highly recommend that. This is particularly bad when you're doing something like a search algorithm, like beam search. And so beam search, as you know from the generation class, instead of picking one high probability, you know, word in your next step, you maintain several paths. And one way that you can fix this is as you make search better, the model scores should get better. So the log likelihood of the output should get better almost all of the time. So you can search with varying beam sizes and make sure that you get a better overall model score at the end. So, and you can even create a unit test testing this as well. I don't think that many people will be re-implementing beam search, so you might not need to worry about that too much. But in case you are doing anything with respect to search algorithms, it's a good thing to know. Cool. Any questions about these two so far? No? Okay. So the next thing I want to talk about, this is something that people think about a little bit less, but it's actually something really important to know because it will affect you, it will affect everybody to some extent. It will affect you to a greater or lesser extent, depending on what type of, you know, system you're building, but it will definitely affect everybody. And that's the mismatch between the function that you're optimizing at training time and the evaluation metric that you're evaluating. And so, like, as I said in the reinforcement learning class, it's very common to optimize for maximum likelihood for training, but there's all kinds of problems with this, you know, with respect to the mistake, it not being sensitive to mistakes, it not being sensitive to your generation algorithm. But even though your likelihood is getting better, accuracy can get worse. And this is a super simple example with image classification on MNIST. And I ran this experiment with like 10 lines of PyTorch code or something like this, maybe more, like 40 lines of PyTorch code. And so here on the left side, we have the loss on the training set and the test set, or the dev set. And here we have accuracy on the training set and the test set. And so Whoops, I showed you the answer. So I was going to do a quiz, but I accidentally showed you the answer. But the problem here is basically because the loss, you're calculating the likelihood of the correct answer. And the likelihood of the correct answer is the probability of getting the correct answer. The accuracy is the number of times you're getting the correct answer. So as you train a model to get more and more confident, it gets better and better at getting more answers correct, but it also gets more and more confident in its answers. And so if there's any example that it's really bad at, it might get very confident in that answer, that bad answer, and the log likelihood of that answer will go up. Or sorry, the log likelihood will go down. So the negative log likelihood will go up is the loss. So basically, the loss that you're calculating and the thing that you care about in the end, accuracy, can be decorrelated. So there's also an interesting example in text generation, and this is part of the reason why we have all these other text generation algorithms like nucleus sampling or top K sampling or other things like this, is actually in a maximum likelihood trained model, better search, in other words, finding a better model score doesn't necessarily give you a better generation result. And this is an example from machine translation from a really long time ago, but it still persists today, which is they did beam search with a larger and larger beam, and the best beam for finding the best scoring output basically was 4, and then the accuracy goes down and down and down as they find a better output. And does anyone remember when we talked about the generation class where this comes from? I don't know how explicitly we mentioned it in the generation class, but basically the problem is maximum likelihood trained models like shorter outputs generally, because as we make the output longer, the probability of the longer outputs goes down. So as you improve the beam, it will start generating shorter and shorter outputs. And because of that, the score goes down because blue score doesn't like outputs that are too short, essentially. So there are hacks around this for beam search, where essentially what you do is you take the average log likelihood of each token instead of the overall log likelihood of each token. And that improves a little bit, but still you can see as you search more, the accuracy goes down. So so that's the general idea here. There's a bunch of ways you can fix this. The most principled way is to use a method like reinforcement learning or something, some sort of structured training algorithm that allows you to train your models so that you don't get these bad outputs. Another way that's much easier is to do early stopping with the evaluation metric as opposed to early stopping with the loss. And by doing this, you would stop here. So you would stop where you get the highest evaluation metric that you care about, instead of stopping here. So that's one way you can fix this problem. Does anyone have an idea about why this might be a bad idea? Why might it be a bad idea to stop here instead of stopping here, for example? Yeah. It's kind of overfitting. It's overfitting in a particular way. But remember here, this is still the accuracy on the dev set. So we're not overfitting so much that the dev accuracy is going down. That would be a different variety of overfitting. But any ideas? Go for it.
We don't want it to be too confident in its wrong answers.
Yeah, exactly. We don't want it to be too confident in its wrong answers. And we talked about calibration, where calibration is basically like how accurate are the probability estimates. So this model over here is going to be really poorly calibrated. It's going to be very confident regardless of whether it's correct or not, and that could be a problem in downstream tasks. There's also another thing that I forgot to put on, that I forgot to put on the slides, but it's an interesting phenomenon that actually kind of a lot of people in interpretability are interested in. It's this grokking generalization beyond overfitting on small algorithmic data sets. And basically what they show is you can be training for a very, very long time and like reducing the loss, reducing the loss, reducing the loss, and reducing the loss. And it's only after a very long time does your model start generalizing well and getting good accuracy. This paper, the types of data sets it's talking about are data sets where you need to get many things in a row correct before you get the final answer correct. So basically you need to get like 20 steps in a row or 50 steps in a row correct before you get the final answer correct. And basically the reason why this happens is because this accuracy will keep going up, but you only get the accuracy of each individual decision will keep going up, but you only get marked like correct after you get like all 50 in a row correct. So this difference can be even more stark when you're talking about things that require like 50 steps of reasoning or like multiple steps of reasoning, but like 50 token generations correct before you get them right. So that's another thing to be aware of. Cool. So now I want to switch gears a little bit to actionable evaluation and how you can evaluate your models in a way that makes it easy to find next steps to be improving. Are there any questions about the debugging part before we get into this part? Okay, if not, I'll go ahead. So my first suggestion with respect to how you can actually, improve systems is make sure that you're looking at the data that you're using. And both bugs and new research directions can be found by looking at your model outputs. So to give one example of a very common mistake that you can make when you're creating a generation algorithm, it's these sort of off by one errors. So like, let's say you implemented a translation system and it's generating outputs like went to the store yesterday, bought a dog. You can immediately look at this and say, hey, this doesn't look like natural English. What's going on? And the problem here is you're doing something like output one, and you have a slice of like 1 instead of 0 here or something like this. And so this is a really silly error that you might just make a mistake on Python on your pre-processing or post-processing or something like this. But the problem is, like, if you look at your blue score based evaluation or something like that, you'll be 1 point worse or 2 points worse or something like that. And you'll be like, oh, I'm 2 points worse. Why am I 2 points worse than the state of the art? And it turns out it was a really like silly thing like this. And immediately you'll see this if you look at your data, but if you're doing all your experiments and just looking at the numbers, it's really hard to tell, why this is happening. Another thing is if you have a good eye and can like just look through the data points, we as humans are pretty good pattern recognizers, and especially CMU students, you're very good and quick at picking up on things. So if you look at the data and pour through things, you can probably pick up patterns about why things are failing. And so you might look and see that compared to some other model, your model is really bad at answering questions about people or something like that. And then you figure out you'll need a better model of people, or your RAG system that you're building for assignment 2 is maybe failing on all the research related questions. So you need to come up with the research, like scrape more research data or something like that. So there are methods to do this more systematically, and this is something I picked up when I was doing an internship at Google, and it really stuck with me for, 14 years now, I guess, 13 years. So a very simple way to do this more systematically than just browsing through things is to randomly sample 100 outputs and look at 100 errors and try to group them into some sort of typology and say, oh, this kind of error is particularly frequent. And this is just one example of a typology that was defined by Villar et al., where they tried to take machine translation errors and group them into various varieties like correct words, filler words, local range, long range, word level, word ordering errors, local range, long range, phrase level, local range, long range, and stuff like this. You can definitely look at previous work and see the typologies of errors that they used. But the problem is, like, systems get better. And actually, I don't think this is a super relevant typology for machine translation anymore. Because machine translation systems, like, they don't make a whole lot of local range word level errors anymore. And rather, we might want to know more fine-grained, like, are they making mistakes on named entities or other things like that? So actually, we did a more recent thing. It's, I guess, 4 years ago now, but it was when people first started saying that machine translation systems are about as good as humans at doing translation. And when we did this, we compared machine translation systems to humans, and we tried to find, different types of things. And we were inspired by Villar, but we recreated our typology based on the things that we thought were, the most important types of errors in like 2020 instead of 2006. So this is really helpful. The reason why it's really helpful is if you can do this, even for a small sample of the outputs that you're looking at, and identify the most like prominent types of errors that you're facing, it often leads you to the most successful ways of improving the accuracy of your systems. Because you might, if you don't do this, you might be focusing on an error type that's not actually an error. It's kind of like if you learned in programming, software engineering or something like that, you should never optimize your code until you run a profiler, because actually your code might be slow in a place that you never expected. And so it's kind of the same principle here, right? So don't optimize your system's errors in a place where like actually it's not having any errors. So that's a general principle here. Cool. Another thing you can do is quantitative analysis. So if you can think of the phenomenon that you choose to focus on, is that phenomenon getting better? So if you focused on something that should improve the quality of low frequency words, you can check if the accuracy on low frequency words is increasing. If you focused on something that should be improving the syntax in a low resource language, you can measure whether it's doing better on word ordering or long distance dependencies. If you focused on improving a search algorithm for, generation or something like that, are the number of search errors that you're encountering being reduced. So depending on what you planned on, improving, it's often a good idea to measure more directly whether it's improving the thing that you think it should improve. One example of, so I basically created, since my experience doing this manually when I was on an internship at Google, I've gradually improved my methodology for doing this. And worked on automating things. And so the first thing I had was a super hacky script that basically writes out HTML files. And then I had something called Explainaboard where we had a leaderboard. And recently, one of the things I've worked on is this together with Alex Cabrera, who's a student here. is this toolkit called Zeno. And this is just an example from machine translation. It's being a little bit slow. But basically what it does is it allows you to look at the data on the right side. And so these are just examples. But you can go in and do things like say, okay, I want to look at all machine translation examples from Hausa. And so it shows you all the ones from Hausa. I want to look at all examples. Let me clear that off. I want to look at all examples where the accuracy is low. And so now I can look at all the examples where the accuracy is low, and I can go in and examine them. So you can also go in and build charts like this. So like, what is the overall performance? What is the performance? What is the performance on different scripts? So you can see which model is doing better at scripts and stuff like that. So, or you can put things side by side and say, okay, I want to find all the examples where ChatGPT is doing much worse than GPT-4. Or like GPT 3.5 is doing much worse than GPT-4. And here we can see that, oh, in this case, it's generating something in the wrong script or something like that. So there's also tooling that you can use to make this easier as well. And the way you use this is you basically create a pandas data frame with all of your data in it, and you upload the pandas data frame with any metadata you want to use, and you can use that. And I think VJ will be having a recitation on this if you're interested in taking a look. Cool. So that is my part, and then we'll be doing Nishant next while Nishant comes up to set up. Are there any questions about the thing that I talked about here? Yeah.
So for Llama, the mini Llama assignment, I've noticed that when I applied regularization, my losses shifted sort of like in the size. But in terms of like their actual pattern, they all converge to 0. Does that make a difference in terms of like what we're expecting when we're evaluating the model loss?
Yeah. So just to repeat the question, it's a great question. So if you apply regularization, will that change the overall expectation for the model loss? So I was saying loss should converge to 0. Once you start applying regularization or weight decay or something like that, it definitely might not converge to 0. Okay. And the reason why is because once you start applying regularization, there is no 0 loss solution. Because in order to reduce the loss, you need to move weights away from 0. But when you move weights away from 0, the regularization loss becomes non-negative. So one thing you can do, however, is measure the losses separately. So measure the regularization component of the loss and the log likelihood component of the loss. And with any reasonable regularization and a reasonably parameterized model, I do think the loss should be getting closer to 0. Like the actual likelihood loss should be getting close to 0 also. Yeah. You were using an extremely small model in the mini Llama assignment, though, so that might make it more difficult. Yeah. And any other things? Okay. If not, I'll.
All right, can everyone hear me? Sweet. Okay, I'm gonna move this. It looks like I'm talking to someone instead of in between both of you. There's one mouse. All right, so hi everyone. I'm going to talk about model interpretability. For those who don't know me, I'm one of your TAs. I'm a first-year PhD student working with Mona Diab on model interpretability. What do I click?
Your mouse should be there now. No, just
Cool. Okay. So what I want you to take away, if you fall asleep, this is too boring. Here are sort of the two main takeaways. One, I want to convince you that model interpretability is important to study. And two, I want you to find this interesting and something you want to explore more. There's a bunch of details here. This is going to be a kind of a whirlwind tour. I'm not going to get super deep into anything. So hopefully this acts as a starting point than anything else. So interpretability in AI, the definition is it's the study of understanding the decisions that AI systems make and putting them into easily human understandable terms. This can mean a lot of different things, and this is often really hard. And the why is to use that understanding to iteratively better design systems that are better, they're more performant, but also those that are more human understandable. So interpretability is this big blob, but there's a bunch of other spheres that intersect with it. This is a super incomplete list. So bear with me, but causality and data integrate with this. There's aspects that are interpretable. There's aspects that matter here. Explainable AI is another thing that you've probably heard. This sits firmly in the interpretability blob and connects with ideas and causality and data too. Model interpretability sits on this kind of other side of things. It intersects a little bit with causality and explainable AI, but is a little bit separate for it and from it. And mechanistic interpretability, which you've probably heard of, it's gotten a lot of buzz recently, kind of sits inside of model interpretability. It's a special case of model interpretability. I hope the mech-interp people agree with me, but so yeah, so historically we've been dealing with really, really, really small models. We had Bayes nets. This is a very small model. If all these are binary variables, this is 8 total parameters, and only 4 of which are independent. We also used to work with linear regression a lot. And in the first case, that's a nice line, can be 2 parameters. The multivariate case, again, that's a small number of parameters. We've moved to more things. We've moved to MLPs that have larger weight matrices, but all of these are kind of digestible and interpretable. So the interpretability world was sort of not super concerned with large, ginormous things, but we're not there anymore. This is a language model. This is still part of a language model. Now it's getting more and more and more hairy, and this is just not interpretable. I mentioned on the first day of class that I hate when we update parameters of models. I also hate when models are this big. And this is a 6-layer transformer. This is way smaller than basically anything that we have. And this makes things very, very uninterpretable. So we'll talk about one way that people sort of 5 years ago started addressing this problem, and this is the idea of probing. So how do we make sense of a giant model? This is one way. So we take our giant model, we cut the top off basically, and now we have this thing. We stick a probe, which actually in a lot of cases looks very similar to a language modeling head. Usually it's a small 2-layer or 1-layer MLP. And we basically treat the model as something that exists, and we only really care about the output of the model. So more specifically, what is a probe? It's a classifier, this green thing here, that is specifically trained to predict some specific property from a pre-trained model's representations alone. So in 2019, Ian Tenney and folks introduced edge probing. So this is a general method. It works to probe different types of information out of a model. So this bottom part here, this bottom part here, you pass in a sequence, you pass it into a model. This is BERT in their experiments often, and that outputs a set of contextual vectors. These contextual vectors can be at any layer. Often it's near the top, but we'll talk about the fact that this can work kind of across layers, and different layers encode different information. And on top of this, you have this MLP that you train to output a prediction. Your model is always fixed in these cases. So you can do things like part of speech tagging, where each specific word you try to determine what its part of speech is. And in that case, these S1 and S2 spans here, only one of them is active because you're predicting for every single contextualized vector, you're predicting whether that thing is a noun or a verb or something like this. You can have other sorts of tasks too, like entailment, where you have two sequences and two spans, and you use the embeddings for those spans. For like sentence 1 and sentence 2, you pull them together in some way, and then you pass them to this MLP, and you see whether the MLP can solve that task. So they did this in another paper. Bert rediscovers the NLP pipeline, and there's a lot going on in this figure. The only major thing here to take away is these numbers that are in this like pink purple color. So these are a bunch of different properties, so part of speech, and a bunch of other things. And what they basically find is that at earlier layers in the model, the things that are closer to the token level representation are more extractable using a probe. And the things that require more contextualized information is extractable later, from later layers in the model. And so here's sort of a brief description of what these tasks are. So the ones on the bottom are more semantic, more contextualized, like semantic proto-roles and relation classification. And then the first few are more, chunking and part of speech tagging and dependency labeling in these sorts of tasks. So there's a bunch of issues with probing, and there aren't as many probing papers now as there were many years ago. And so if your probe, let's say your probe works, it's possible that the representation actually encodes that information. It's also possible that it doesn't, and the probe solved the task by itself. Keep in mind that you're learning this probe, you're training this probe on labeled data. Let's say your probe doesn't work. Does that tell you anything? Maybe not. Maybe the representation lacks the information, or maybe your probe isn't actually able to disentangle that information from your representation. Maybe the probe doesn't have the right function class. Maybe you poorly trained your probe. There's hyperparameters for your probe. So oftentimes your probe doesn't give you that much information. There's more problems too. So often we want to probe tasks themselves, and that requires a lot of supervised data. But we can't collect a lot of supervised data, so we collect some of it. And then that instead produces this convenient sample that we have that's a data set that is a convenient sample of your task. So really what you're probing is the data set. And so with all these limitations, it's fallen out of favor a little bit. It's still very, very useful, but it's fallen out of favor as like a core model interpretability idea. Also, probes designed in this way are correlated. They're correlative, not really causative. So your underlying model is trained in a specific way. All of that information is disentangled and kind of thrown away, and you're only looking at the output representation, and you're saying, is my output representation correlated to the thing that I'm training this probe for? There's no notion of intervening on this latent space. There's no notion of causation, really. So you're just seeing whether your representation is correlated with your property that you're probing for. And with these limitations, the community's moved a little bit away from this area. There's a bunch of other probing work. So a bunch of people aim to solve a bunch of these problems. And for the sake of time, I'm not going to go into all of these, but I'd encourage you to look into these. For some of these problems, they're able to control for like the complexity of the probe and things like this. But even despite that, probing is sort of slowly kind of falling out of favor. So before I move into model interpretability, are there any questions on probing? All right. So what is model interpretability? So this is my definition here. This is the study of understanding the internals of models, for example, their weights and activations, putting those insights in human intelligible terms and using that insight to both patch current models and develop better ones. If we're not sort of able to do both of these things, patching current models and develop better ones, we're kind of doing interpretability for interpretability's sake. That's nice and fun, but it's not as applicable for the community. So you've probably heard of the term mechanistic interpretability. It's, in my opinion, a subfield of model interpretability. And this is sort of my definition. It aligns reasonably well to the core mechanistic interpretability people. But it's the study of reverse engineering parametric models, often neural networks, because that's what we use, from their learned weights into more human interpretable algorithmic units. And often they call these things circuits. And these are basically functions that you can describe in a human interpretable way that sit inside models. There's a bunch of notable work, again, for the sake of time, I'm going to just briefly talk about them. So the first one is they look into analyzing small MLPs and transformers to build out the intuition of what circuits exist. And a lot of this work came out of earlier work on LSTMs and doing similar sorts of things with LSTMs. And they find a bunch of things. One thing that they find is this idea of induction heads. And these induction heads, they say, is sort of helps prove why models can do in-context learning. So an induction head is something that it's a specific attention head that kind of allows you to, when given a prefix, allow you to kind of copy the necessary resulting token from the underlying training data that the model's seen before. So in context learning, what you generally provide is some sort of prefix, and then you provide some example, and hopefully, you can classify the thing or something like this. It's saying that there's these attention heads loosely that exist that are able to copy or unearth that information for a specific context. Other things that they've done is on neurons. So this polysemanticity. So what this kind of means is that your neuron is you have a set of neurons in your activation space. So let's say at layer 10 in your model, you have an output. And so your activations is, let's say, 1,000 dimensional here. Each of those 1,000 individual neurons may represent more than one specific feature. And so they talk about this in that context, and this is kind of a theory, but you can think about trying to process input. And when you're processing a vocab of size 50,000 or 250,000, at some point in the model, we're actually compressing it down to the hidden dimension. And so in some cases, that looks like you're trying to compress a much richer feature representation down into a smaller set of neurons. So it is reasonable to believe that a specific neuron will represent multiple of those features. And given the structure of our weight matrices, it is the case that if they are representing more features than number of elements in the actual, or the number of neurons in the activation space, then many of these features are linearly dependent. And so we're not really able to utilize them that well. They talk about this. They don't talk about this in the best way, but it seems kind of clear to me that since you have embedding matrices that are not square, that these neurons have to exist, and they have to incorporate multiple features at once, multiple redundant features at once. So before I move on to the rest of model interpretability, any questions about mechanistic interpretability? Yeah.
You mentioned that you apply some sometimes and then others, where, like, for instance, the induction has worked for different types of arguments.
So most of their studies are for a very small set of models, and most of these are old GPT models. There have been a few works, like in the last couple of months, on doing this for the llama-based models. It seems like this is a more general phenomenon for language models. It also is the case that certain attention heads specialize, and we'll talk about them a little bit. in the activations part. But yeah, they're not like all attention heads aren't created equal, even though they start this way. And it seems to be a general principle across.
And one other thing, you might know about this better than I do, but I think there are some preliminary works that say that transformers seem to be particularly good at doing things like induction heads compared to kind of recurrent models. And there was a paper really recently about comparing like Mamba in transformer-based models. Mamba being a kind of more like closer to a recurrent network, which we're also going to talk about in class. But so I think there's some indication that transformers actually kind of are key, or are at least like better at kind of in-context learning than other architectures are. So there is some interesting implications of that, which is like, well, if transformers are good, what's better than transformer? Yeah, like naturally learning this sort of thing. So
they're good at, they're like really good at copying and like maintaining information, like more so. And yeah, I think it'd be cool to like be able to, I don't know how to do this, but be able to extract that kind of information, like what of the transformer is actually helping it do this copying mechanism, or like being a better in context learner. Then we can develop a better structure, a slightly better structure than a transformer. Hopefully if someone comes up with that soon. But cool. Any other questions? All right, so let's move into model interpretability. So there are weights and there are activations. I mentioned these are the two things. These are the two things that we're going to look at. So what can you do with the weights of an already trained model? Really, you can just edit them and then kind of see what happens. The activations, similarly, you can look at the activations for different inputs. You can poke them with a stick and see what happens. A lot of my research is poking models with a stick and looking at the activations. It's like predominantly what I've done, so we'll talk about that. And the technical term for this is intervening on them by adding some vector or other sort of manipulation to the latent space. But really what you're doing is like poking with a stick. So when you look at weights, one class of methods or area is on model editing. Fine tuning is like the most extreme version of model editing. Usually these things are much more targeted. So in the model editing sort of landscape, your goal or your target is you have a concept or a specific fact that needs to be changed in the model. And your approach here is you update or edit the weights of the model to edit the model's belief of that fact or concept. And ideally, you do this without changing any of the other behavior of the model. So for example, let's say you're trying to say that Graham is no longer a professor at CMU, but is a professor at Stanford. You don't want every single person at CMU to now be a professor or now be affiliated with Stanford, right? Graham, please don't go to Stanford. So here's one approach, a paper that came out a couple years ago. There's a lot of work down here in the model editing world. I'll give you sort of a really brief overview of this. But basically, they have facts that they want to manipulate. So for example, the example that they give in the figure is they want to associate the Space Needle with Paris. The Space Needle is a cool needle in Seattle, has nothing to do with Paris, but Paris also has a tower, so yeah, it's close. So they use causal tracing to isolate the causal effect of the individual hidden states for this fact. So they basically continuously perturb the input, do a bunch of forward passes, and sequentially find the specific hidden states that are associated kind of with this fact. Then they make an edit, and their edit looks like this thing on the right. So they treat this pair, Space Needle and Paris, as this key value pair, where Space Needle is the key. You pass this into this weight matrix, this original part of the model. You want this now, instead of outputting Seattle, to output Paris. And they have some nice math and a closed form solution to identify this. This is super expensive because they have to, the like causal tracing part, they have to do a bunch of forward passes. And they make this a little bit better in future work. They also do sort of a more comprehensive edit. So these are kind of like some of the things you can do. I'm less excited about model editing. There's there's some work on model editing, sort of, it's hard to control what other things break. And there's some work with when you edit a specific fact, things start being weird and being biased in other ways. And so, yeah.
Just to clarify, do all kinds of factual information like X is in Y, like, would they all correspond to the same layer, or is it just with the specific like example?
For this specific example, it looks at this specific point. For every example, they'll probably find different regions and a different degree of manipulation. And yeah, that it gets a little unprincipled kind of quickly. It's not like they're able to find, you know, a specific attention head that, or a specific layer or specific weight matrix that corresponds to like all, yeah, relations of a specific type. Any other questions? For, yeah.
This is actually just a question, if you know, it seems like more frequent facts might appear in more places in the model. Do you know if that's actually the case? Or?
I have no idea, but I would imagine that it probably could occur in more places, but also a lot of the information is redundant anyway in the model, especially for larger models. So you might have to make targeted interventions in multiple places, but it's possible that one intervention in one place sufficiently destroys like contextualized information in other places if it's close. It depends on how big this intervention is, if it's like hitting it with a hammer rather than some like nice fine-grained thing. But that'd be a good experiment to see. Any other questions? All right, so we'll move into the stuff that I'm most familiar with in some of my work. So looking at activations. So this is work I've been doing for a while, this idea of steering vectors. So I mentioned I poke models with stick. Steering vector is that stick. So it's basically a fixed length vector that steers a language model to generate a specific sequence exactly when added to the hidden states of a model at a specific location. And I'll read this again. There's a very like specific form that I wrote this in. So it's a fixed length vector that steers a language model to generate a specific sequence exactly when added to the hidden states of a model at a specific point. So this is different than a soft prompt or different than a model editing sort of approach. In this case, there is a vector that corresponds to a sequence, and that vector doesn't correspond to any other sequence. There could be multiple vectors, and it turns out there are multiple vectors that correspond to that sequence. It'll be a little bit clearer based on how we extract these things. So this is the stick that we're poking the language model with. So how do we extract them? So this is GPT-2. Basically, this Z steer thing on the left. This is the steering vector. This gets initialized randomly with small, like in a reasonable way, uniformly and small. And for any sequence, a specific sequence that we want the model to generate, we optimize this steering vector, Z steer, to generate that sequence, keeping the rest of the model entirely fixed. So think about it as we're nudging a frozen model to be able to generate a specific sequence at a specific time. And we have a lot of different options on where to inject the steering vector. We can put it basically anywhere in the model. We can put it at any time step, any number of these things. In practice, providing it just at the first time step and somewhere in the middle of the model, basically not the first layer and not the last layer, works pretty well. And so more formally, forget the kind of notation, but right here, we initialize this Z steer, and for a few iterations, we do forward passes. First, this starts as random, and then this gets closer and closer and closer to being able to generate the sequence. And eventually, we get to a point, and this n is pretty small, it's like 8 or 10 or something like that, for most sequences. We get to a point where we have found this stick that is allowed to poke this model to generate that sequence exactly. Now, when we greedy decode from the model, we pass in just a beginning of sequence token and this Z steer, the steering vector, and it's able to uncover a whole sequence, that whole sequence that we had at the beginning entirely. this is weird and interesting because in a lot of cases, in like the prompting world, in the soft prompt world, usually you need a pretty large width of a prompt to be able to do things with. And this generally in that structure, you're doing a specific task and you're providing kind of a large prompt to do this with, large soft prompt to do this with. This often has a width of 50 and a length of the hidden size or the embedding size of the model. In our cases, all of our steering vectors are width 1, and they're of just the hidden size of the model. So what ends up happening, actually, before I go to results, any questions? This is a weird setup and weird relative to what other people do. So happy to take any questions. Yeah. Similarly, if your prompt was of a specific type. So the prompt here is a continuous vector passed in, it's a single length with hidden size continuous vector. So it's kind of like maybe collapsing your prompt into this, compressing it into this tiny vector. You can think about it that way, yeah. Any other questions? Yeah.
So like, for instance, this would be like free. I'm just thinking like using steering vector would also be pretty good for like things that are complicated.
Potentially, this is something that I wanted to work on like a year ago and didn't get the sufficient buy-in, and then had to apply to grad school and all these things. So it went by the wayside, but definitely something to pursue. There's a lot of scope there. But any other questions? All right, so move over to results. So we can find steering vectors, and that's interesting. And we can find them pretty easily, and for most sequences, even sequences that the model hasn't seen before, the underlying language model hasn't seen before. It also works for, and this is kind of a negative, but it also works for random sequences of very small length, but it's harder to find. So you can imagine if your steering vector is basically a giant bulldozer, it doesn't matter what your model has learned, similar to the probe situation. If you can compress all that information of that sequence into the vector, you don't really need the language model. So there are cases when you're looking at sequences of length like 5, 7, 8, something like this, you can uniformly sample from the vocabulary at random with replacement, generate utter garbage, and find steering vectors for them. Takes a little while, but your model is complex enough that you can basically bulldoze your model to be able to do this, even if that sequence is incredibly low likelihood under the model. But it works better for things that are higher likelihood under the model, predictably. I think the thing that surprised me the most was these steering vectors themselves have interpretable properties. So distances in steering vector space reflect semantic similarity. So if you have two sentences that are close, they're also close in steering vector space. That's kind of nice. It does better than, for example, the representations one would use for probing. So mean pooling BERT hidden states, like we looked at before, those do actually worse than steering vectors. Just a bit surprising. Style transfer is possible with simple vector arithmetic. So it'd be nice to say that I have a sequence, I want to subtract, negativity and add positivity for sentiment or other sorts of styles. We can do this, and we can do this reasonably well in steering vector space. We can also decode from interpolations in the latent space. So you take two steering vectors for two sequences, you look in the middle of them, you linearly interpolate between them, and you decode. If the space is kind of weirdly peaky, then you would have issues, and what you would generate is garbage. And there's no guarantee that the space should be reasonable in between them, but it turns out it is. Here's an example of one of these style transfer cases. So very, very simple, easy sentence. We found steering vectors for the taste is excellent. And we took a sample of 100 positive sentences and 100 negative sentences, found their steering vectors, took the mean, and thought that, that looks like the positive concept steering vector, and negative concept steering vector. We just did vector arithmetic, just did current steering vector, plus negative minus positive, and we got the taste is unpleasant. And similarly, in the reverse directions. It turns out that the magnitude matters because for every single sequence, there's kind of an n-dimensional ball around that steering vector that we found that also decodes that specific sequence. And so that shows that the space is kind of reasonably well formed. There's of course, a lot of weird sort of areas. And so if you go poke around in steering vector space and sort of try to sample from it, eventually you'll find some weird edge cases and some garbage and repeated text and little things like this. Any questions here before I kind of rapid fire through the last few things? Yeah. Yeah, so we went beyond this. There was in these specific experiments, we looked at the middle of GPT-2. So this was like layer 6, layer 7, and at the first time step. We didn't do any like magnitude scaling. And so you can imagine if you put a giant vector in there, the rest of the model has never seen something of that magnitude. So it's now in a weird state and it's just going to break. So if you put this to like, I don't know, 500 or something like this, it breaks. It just has no idea. It's like basically like telling the rest of your model, hey, it's like a completely untrained model. It looks similar to like random performance. You get repeats and things like this. Smaller, you end up staying in this ball for this sequence. Two seemed pretty reasonable, but we didn't spend a lot of time. Just like the day before the paper was due, and we're like, 2 seems reasonable. We went to 3, we went to 5, 10 broke, 5 somewhat broke. 2 seems reasonable. Decent science, hopefully. Cool. So I'll talk about a similar type of work that came out more recently on inference time intervention. So basically, they use some of the ideas that we talked about earlier. They use linear probes to find attention heads that correspond to a desired attribute. They did this for truthful QA. So their hope was to find truthful directions in latent space. And then they shifted the attention head activations during inference along the directions determined by the probes. So what this kind of looks like is you take your attention heads, you probe them, so you stick a classifier on top. This classifier learns to disentangle sort of truthful and untruthful, and now you have a hyperplane, and then you can move orthogonally to this hyperplane in the direction depending on which way you want to shift. So if you want to move towards truthful, you can move in that direction or away. And they do this, and it works pretty well. I think they do this for a GPT model and maybe a llama model, but can't remember the exact details. And it's a similar intervention. They basically add this vector that they found, and they have a little note on scaling. If the magnitude of the thing is too much, things break. So they like hyperparameter search for the sort of magnitude of activation. But it's sort of a very similar approach to what we did, but this focuses on specific attention heads. And they don't do this for all the attention heads. So back to like your question earlier, do attention heads specialize? It seems like they do. And so there are many of them that have like no probing accuracy or limited probing accuracy and actually are like distractors for the truthful direction. Any questions here? Cool. So more activation manipulation. So there's some work recently on contrastive steering vectors. So the way we did this like sentiment steering was we had some positive sentences, some negative sentences. They weren't tied together in any reasonable way. We found their steering vectors separately. You could imagine the case, and maybe a more useful case, with 2 prompts that you can design that go 2 different ways. You can sort of find their representations and do the manipulation, the differences here. like individually rather than for a whole concept or a whole attribute. And the value here is your context is preserved. So if you're doing something like, you're doing retrieval-based things now, you have some sort of document and then you have a question. If your question sort of, if you want to ask it in two different ways for two different things, this would be a much better approach if you want to use steering vectors than the stuff I was doing. And it seems to work a little bit better. They didn't compare against our things because it's not like an apples to apples comparison, but it seems to work better and be more general and be more useful. Any questions? Cool. So what can model interpretability give us? These are my concluding remarks. So hopefully we get a better understanding of how language models work, their internals, their structure. We get to understand kind of why they do really well. This is still like very, very unclear. And hopefully we find lightweight methods to control and steer models. As models become more and more useful and impact more users, we need better ways to control and steer them. And it's unclear how much industry will devote to these things. So it might be the role of academia to do more science in order to figure out how to control and steer these better. And hopefully we can also find potential alternatives or complementary methods to do alignment. RLHF is kind of expensive. And if we could do this with limited data and exploit structure and information that's already in the model, more so than these methods, maybe we can align them better. And these things don't have to be alternatives. They can be complementary to RLHF. Here's some resources. This is an extremely incomplete group, but here are some folks that work on model interpretability. There's many of these. I cited some work from some of these teams, but there's a lot of people working on it. And in the last year, there's been kind of an explosion, especially in the mechanistic interpretability kind of world. Sasha Rush had a recent tweet that asked prospective grad students what is the topic that they're most excited about, and mechanistic interpretability was the thing that seemed to have won out. So I encourage you to kind of dive into this literature and read some of the papers if you're excited about it. And yeah, thanks for your attention. And that's all I have.